Hello and welcome to Biological and Physical Chemistry. My name is Stephanie Schweiker and this is the last lecture for organic chemistry. So it's topic 1.5, amines and heterocycles. So up until now we've been looking at oxygen containing compounds such as your alcohols, your carbonyls and your carboxylic acids. Now we're going to be looking at nitrogens and amines. So nitrogen compounds with a nitrogen and R groups or hydrogens coming off it are amines. Okay, so the simplest one is ammonia, which is NH3. So you'll notice that in the pictures when we draw our amines we have these two dots on top, so we've got a lone pair. So the lone pair allows your amines to act as a nucleophile and it makes them basic. So nitrogen containing compounds form one of the largest groups of compounds. So there's lots of naturally occurring nitrogen containing compounds known as alkaloids, and lots of biological molecules contain nitrogen. So some examples are adrenaline, your amino acids, DNA and RNA. And a lot of drugs contain amine functional groups within them. So codeine, caffeine, quinine, cocaine and amphetamine are a couple, just to give you some examples. So the nitrogen is sp3 hybridized because it's got the 3 bonds and the lone pair. They're weak bases, like I said, they act as a base, so their pKa's are between 9 and 11. So remember, the smaller the pKa, the stronger the acid. So the larger the pKa, the weaker the acid or the stronger the base. So they've got large pKa's, so they're not very acidic, so they're weak bases. So the amines can be primary, secondary, tertiary or quaternary. Okay, so examples for a primary is your ethylamine. So we've got a methethylamine. We've got the diethylamine, which is a secondary, so we've got 2 ethyl groups and a hydrogen. Triethylamine, we've got 3 ethyl groups and a nitrogen. And if we add another ethyl group in, we get an ammonium salt. So we get a quaternary nitrogen with the 4 ethyl groups. So it's tetraethyl ammonium iodide because it's made an iodide salt in this case. So you can get aliphatic and aromatic amines. They can be either alkyl or aryl substituted. So here is your alkyl alcohol. So this one's a tert-butyl alcohol, a tertiary alcohol, and this one is your tert-butyl amine. Okay, so it's the same, we've just changed the alcohol to amine when we've done our nomenclature. This one here is a tertiary alcohol. So the carbon that's bonded to the alcohol has 3 groups coming off it. When we look at nitrogens, so amines, we look at what's coming off the nitrogen, not what's coming off the carbon next to it. So this one here is a primary amine because it's got 1 R group and 2 hydrogens coming off the nitrogen. Okay, we've got aniline, which is a primary aryl amine. Okay, so aryl is the aromatic and it's an amine. We've seen aniline in the last topic, 1.4, when we looked at benzene and its derivatives. And here we have a tertiary alkyl amine, so a trimethyl amine, so we've got 3 methyl groups. Okay, so amines that can form cyclic compounds are called heterocycles. Okay, they're not necessarily aromatic, but they can be aromatic. So again, last time we saw some aromatic examples. So we had our pyridine, pyrrole, and as examples last time, and they are aromatic. And other ones to add to your list are piperidine and pyrrolidine. Okay, so here it's 1, 2, so it's a secondary heterocyclic amine. Here again 1, 2 coming off the nitrogen, so it's a secondary heterocyclic amine, so it's a heterocyclic. So a heteroatom is an atom that is different. Okay, heterocyclic amine. This one's a tertiary, so we've got 1, 2, 3 bonds. So the double bond does count. Okay, so we've got a tertiary here. And this one's aromatic. We know it's aromatic because it abides by the rules for the aromaticity. So we've got 2, 4, 6 electrons, which fits into your 4n plus 2, giving your n a whole number. And we've got the pyrrole, okay, again is aromatic, and we've got a secondary amine now. So we've count these 2 nitrogens and those 2 there. So remember, when we're looking at the nitrogen, we count the lone pair on the nitrogen if the nitrogen is bonded to another substituent that's not part of the ring. Okay, so this hydrogen on the pyrrole is actually pushing those lone pairs into the p kind of orbital space, whereas in the pyridine the nitrogens are out on the more planar kind of face, pointing away from the cyclic ring. Okay, some common examples. So we've got our primary, so this nitrogen has 2 hydrogens and 1 R group. Primary aromatic, which is aniline. We've got conene. Okay, so this is a nitrogen with 2 coming off it and a hydrogen, so it's a secondary. Okay, and nicotine, we have 1, 2, 3 groups coming off the nitrogen, so it's a tertiary amine. Okay, this is aromatic, 2 heterocyclic, and this has got an aromatic here as well, so we've got 1, 2, 3, so a tertiary amine in the aromatic ring. Okay, so some other examples are your penicillin. Okay, so we've got amide and an amide. So an amide, remember, is a nitrogen with a carbonyl. Okay, so we've talked about these before, so nitrogen with a carbonyl. So penicillin has an amide. Okay, here we've got a nitrogen with 3 R groups coming off it, so it's a tertiary amine, and it's got a heterocyclic because it's a ring with a nitrogen in it. Adrenaline, we've got a secondary amine, okay, and it's aliphatic. It's got no aromaticity and no cyclic structures. Benzocaine, okay, so we've got the NH2 coming off the benzene ring, so that's a primary aromatic amine. And vitamin B6, we have 2. We've got 1 in the ring and 1 out of the ring, so this is an aromatic and this is an aliphatic, and we have a tertiary and this one is a primary. Okay, so let's have a go at the checkpoints. So classify each of the nitrogens within these amines as primary, secondary, tertiary or quaternary, and state whether they are aliphatic or aromatic. Okay, let's go through the answer. So we have 1, 2, 3. This one here is aliphatic tertiary. Okay, this is an aromatic, 1 secondary, and this one is an aromatic tertiary. Okay, so these 2 are aromatic because they're connected to aromatic rings. This is aliphatic because it's away from the aromatic rings. Yep. Okay, so nomenclature for your simple amines. Okay, so it's similar to naming your alcohols, okay, but instead of ol, you write amine. Okay, so it's like the example we saw a few slides ago. So we got tert-butyl amine. That's kind of got a little bit of common nomenclature out the front, but we have that amine here. So cyclohexyl amine, so we've got a cyclohexyl ring and we've got an amine. Here we've got 1, 2, 3, 4, so it's butane, 1, 4 diamine. Okay, so if it isn't the parent group, you do the N substitution. So you write N and then you put it out the front. So it's an N-alkyl amine. So we'll see some examples of what we mean in a minute. Okay, so for amines containing multiple alkyl groups bonded to carbon, the amine is named based on the alkyl group. Okay, so now we have it where it's not the highest priority and we call it amino. So carboxylic acid 1, 2, 3, 4. So the carboxylic acid higher priority, start out numbering from 1 going to 4. 2 is the amine, and when it's not the highest priority we call it an amino. So it's 2-amino-butanoic acid. Okay, so now we've got a benzene ring in the middle. We've got benzoic acid, which is our highest priority, and we've got 2 nitrogen NH2s coming off it. So it's 1, 2, 3, 4. So 2,4-diamino-benzoic acid, or we could call it ortho-para-diamino-benzoic acid. Okay, so we've got a ketone, 1, 2, 3, 4. So it'll be 4-amino-but-2-one. Okay, so now when we have the secondary and tertiary amines, we're getting into this N-alkylated N-alkylated nomenclature, sorry. So we can have symmetrical or unsymmetrical amines. So when we have symmetrical, we just say di or tri to the alkyl group that's coming off it. So this one here would be diphenylamine. This one would be triethylamine. Okay, when they're unsymmetrical, we name them as N, and then whatever the group is, it's the lower priority. Okay, so the root name here would be 1, 2, 3, so it'd be propanamine, and it'd be meth-eth, so it'd be N diethyl propanamine. Okay, so you say nitrogen, nitrogen, diethyl. So it's the same as before when we were doing simpler nomenclature back in CLS, and we talked about if we had 2 chlorines coming off a carbon, we'd have to number the carbon, so it'd be like 2,2-dichloro. So this is the same, so it's NN diethyl, and then propanamine, which is the parent name. So with this one here, the highest priority, or the biggest group, is this cyclohexane ring, so it would be cyclohexanamine, and it would be N-methyl N-ethyl, and this is alphabetical out the front, so it's N-ethyl N-methyl cyclohexanamine. Okay. So here we've got some common heterocyclic compounds. So we've got pyridine, pyrimidine, pyrrole, imidazole, quinoline, and indole. Okay, so quinoline is commonly used for tuberculosis drugs. Just as a little bit of information there for you. The nitrogen heterocyclics you'll find are very common in medicine and okay, so let's have a look at some heterocyclics. So we've got some common ones here. So we've got pyridine, pyrimidine, pyrrole, imidazole, quinoline, and indole, and they're parent compounds, and you can get substituted heterocycles, and depending on where the substituent comes in, you look at all the different numberings. So with the pyridine, you number it 1, 2, 3, 4, and then there's the similar patterns for the other ones. So they get quite complicated. So remember your rules for aromaticity. So you have to have 4n plus 2. So each one of these are aromatic. They all abide by the 4n plus 2 rule. Some of the nitrogen lone pairs are in the ring, whereas others are out of the ring. Okay, so remember, when a nitrogen is making a single bond to something that's not in the heterocycle, then it's pushing the lone pair into the system. So the same as we've discussed before. So this nitrogen lone pair is out of the system, whereas this nitrogen lone pair is into the system. So that's why we get the 2, 4, 6 electrons. Okay. So some of these compounds you can have with other heterocycles. So pyrrole is also known as furan and thiophene, depending what heterocyclic atom you've got in there, so nitrogen, oxygen, or your sulfur. Okay, so let's have a go at some checkpoints. So name the following amines using our UPAC systematic nomenclature. Okay, so the first one's just counting up the carbons. So 1, 2, 3, 4, 5. So pentanamine. Okay. 1 you can put out the front if you want. You can also write it as pentylamine. So pentan and pentylamine is the same thing. Okay, so looking at this next one here, we've got a CH2 with a benzene ring, which is, remember, a phenyl is just a benzene ring, and a benzyl is a CH2 with a benzene ring. So this is a benzyl amine, okay, and this is a trimethyl amine. Okay, so let's draw the structures for the following amines. So 4-nitroaniline, so one from last week, and N-methyl-2-hydroxypyridine. Okay, so we've got our 4-nitroaniline, same as last week, and our pyridine ring, okay, is a 6-membered ring with the nitrogen, and it's N-methyl, so methyl coming off the nitrogen, 2-hydroxy, so 1,2-hydroxy. Okay, and this one goes back to where did we do for pyridine? The pyridine. There it is there. Okay. Okay, so let's look at the basicity of amines. So the chemistry of amines is dominated by the lone pair. So the lone pair can act as a nucleophile or it can act as a base. Okay. So acting like a base, it can react with acids to form acid-base salts, and acting like a nucleophile, it can react with electrophiles in polar reactions. So like we've talked about before, nucleophilic attack is the sort of thing that would happen with your nitrogen-containing compounds. So attacking carbonyls. So amines are much stronger bases than alcohols and ethers. Okay, and remember, the stability of the base has got to do with the availability of those lone pair of electrons. Okay, so the more available they are, the stronger the base. Okay, so when you put ammonia in water, you have the lone pair attacking the hydrogen and acting as a base. Okay, so making an alkyl ammonium salt, and you have OH minus being produced. So this is the weak base, and this is the conjugate acid. Okay. So this is just here to remind you of your KBs, your PKBs, your pKa formulas from last semester. So remember, your KB is your products over your reactants. Water's a liquid, so we don't include that. So it'll be NH3 with your R, okay, so plus and OH minus over your NH2R, okay, and your pKb is the negative log of your KB, and your pKa and your pKb equals 14, and your Ka equals 1 over your Kb. So you've got an inverse relationship there. Okay, so let's have a look at the basicity of some common amines. So the smaller the pKa, the stronger the acid. The smaller the smaller the pKb, the stronger the base. So the smaller the pKa, the stronger the acid. The smaller the pKb, the stronger the base. So if we look at these compounds here, we can see that there's a little bit of a trend. So we have our ammonia, which is a pKb of 4.7. Okay, so it's, you know, it's a pretty small number, but not as small as something like your methylamine or your diethylamine. Okay, so as soon as we've got aliphatic R groups, so primary or secondary alkyl amines, we're getting smaller numbers, and we've got our aroamines, we're getting bigger numbers. So it's saying that the alkyl amines are the stronger bases, and the aromatic amines are the weaker bases. Okay, and remember, the strength of the base is determined by the stability of its conjugate acid. So the more stable the conjugate acid, the stronger the base. So looking at the conjugate acids, this can help explain the reasons behind this. So if we look at NH3, if it was to pick up an extra proton and become the acid, so act like a base to become the conjugate acid, we'd get NH4 plus. Okay, and that positive charge is just being held by hydrogens there. Okay, whereas if we had the methylamine and it picked up an extra proton and made the N plus charge, it's more stable because the nitrogen is being helped out by the carbon to stabilize that positive charge, so it's able to hold it for it. Okay, so this one is more stable than that one. So because this conjugate acid is more stable, the base is stronger. Okay, the least stable one is this aromatic amine. So when we have aniline and it's protonated to make the conjugate acid, we have NH4 plus, so NH3, sorry, plus the R group with the plus. And you've got a positive charge next to all these delocalized electrons. Okay, the reason that your aroamine is incredibly stable without that positive charge will be shown on the next slide. So it goes back to those resonance structures and delocalized electrons and the lone pair of that nitrogen being fed into the aromatic ring. Okay, so that positive charge is not stable. Okay, so primary, secondary and tertiary alkyl amines are 10 to the 6 more basic than aroamines. So it's quite a big difference there. And the difference is attributed to the resonance stabilization in the aromatic systems. Okay, so the more resonance structures you can get, the more stable that is. So this NH2 attached to the benzene is very, very stable. Okay, so that means that it doesn't want to form the conjugate acid. Okay, and the ability to form that conjugate acid relates to the strength of that base. So it's a weak base because it doesn't want to form the acid. It doesn't want to act like a base to form the acid. Okay, so the basicity of aromatic amines can be influenced by the substituents that are bonded to the ring. So if we have an electron withdrawing group, so such as NO2, we have less resonance stabilization because we've got the electrons withdrawing from the amine, making it less basic. Okay, so the electron withdrawing group is pulling electrons away from that nitrogen, making it less able to undergo nucleophilic attack or act like a base. So electron donating groups, okay, would make it a stronger base. So So let's look at amides. So amides are non-basic compared to amines. They're non-basic because they don't react. They don't like to be protonated in water, and they're very poor nucleophiles. The reason for this is because we have this conjugation resonance stability over this amide bond. So we can have the double bond on the oxygen and the single bond on the nitrogen, or we can have the double bond to the nitrogen and a single bond to the oxygen. So we've got a little bit of delocalized electrons, so it's very stable and it does not want to react. So protonation is less favoured. So how do we make amines? So going on some chemistry that we've already done, we can use reduction of nitriles to form amides. Sorry. Okay, so we can do reduction of nitriles or reduction of amides to form amines. So we've got alkyl halide, okay, substituting it with a cyano, so a CN group, we can get the carbon nitrogen triple bond, and then reducing that all the way down to the carbon with a single bond to the nitrogen and 2 protons on the nitrogen. So we would get a primary amine. Another way of making it is starting with carboxylic acid, okay, thionyl chloride to change it to a chlorine group here, and then the chlorine group is replaced by an NH2 with just NH3. And then this can be reduced, okay, down to the primary amine. We can have SN2 alkylation of alkyl halides. Okay, so this is when you have your nitrogen and we have an SN2 reaction, a good leaving group, and then we get our ammonium salt, our alkyl ammonium salt. And if we then treat that with base to get rid of the salt, we would get our tertiary amide being produced. So this is going back to topic 1.1. This is probably 1.2 for these two here. Okay, and the new reaction that we're learning this week is the reductive amination. And this is one of the nicer reactions to do, and we use this quite a lot in our research lab because it's a nice stable way of making amines, and the chemistry is easy, it works well, and it's relatively non-toxic as far as chemistry goes. Okay, so you can start with a ketone of some sort, and if you add NH3 and then sodium borohydride, you can form the imine, so changing this oxygen to a nitrogen and then reducing down that double bond to the NH2. Okay, so that would be the synthesis for an amphetamine compound. Another one is, so if you start with a ketone, if you want to make a primary amine, secondary or tertiary amine, you would use a different type of nitrogen compound. So if you want a primary, you'd use NH3. If you want a secondary, you'd use RNH2. And if you want a tertiary, you'd use R2NH2. Okay, so when we do this reaction, we lose one of the protons. Okay, and we're gaining a carbon. So a secondary nitrogen, a secondary amine will give you a tertiary amine. Okay, primary would give you a secondary, and a nothing would give you a primary. Okay, so reductive amination is used in the synthesis of aniline, which is an amino acid. So this is a biochemical reaction. So starting with pyruvic acid and ammonia, you'll get your imine intermediate, and then you have an enzyme that reduces down that imine into your aniline, so your amine. Okay, let's look at the mechanism. So first of all, we have our carbonyl. We have nucleophilic attack from the nitrogen, and then we have the protonation of that carbonyl bond. Okay, so we get our alcohol and our amine attached. What happens then is we have the dehydration and we have the imine being formed, so the double bond to the nitrogen. So when you do this reaction, you add your two starting reagents together, so your ketone and your amine, you stir them overnight and you get an imine formation, and it makes a nice colour. Depending on how conjugated your system is, you'll get different colours. So with this particular one here, you probably wouldn't get much colour, but you would get a different colour because you've got more double bonds in the system. They're nice and easy to monitor by TLC, which we'll learn about in the lab this week. Okay, and then you'd come in the next morning, you add in your sodium borohydride. Okay, so you're reducing agent and leave it for an hour or two, and you get your amine out at the end. Okay. So purifying amines. So purifying amines can be done based on the basicity of your amine. So knowing that amines act under certain conditions a certain way. Okay. So if we've got an amine and a neutral compound, what we can do is dissolve it in some acid, okay, and we would get the NH3 R NH3 plus. So we could make it charged by putting the the nitrogen or the amine in an acidic condition. We would make that charged. We'd make the salt, and then washing it with some sort of organic solvent such as ether will drag the neutral compound that doesn't get charged in acidic conditions into the ether layer or the organic layer, and then you would have your amine charged in an aqueous layer, so using the polarity of those two, so they'd form two different layers, and you would drain them both off, and then you would put in your aqueous layer again into your separation funnel, and you would neutralize it back down so that you put in some base, so that way you could get rid of the charged and go back to the amine that you originally have, and then using your organic solvent again, so ether in this case, shaking them up and then separating out the two layers. In the aqueous layer, you'll just have the salt that's left over. So if you used hydrochloric acid and sodium hydroxide, you'd have sodium chloride. So it's just a brine kind of water. And in your ether layer, you'd have your amine. Okay, so how would it work if you wanted to design a method for separating nitrobenzene from aniline, and diethyl ether was the organic solvent that you used? So let's have a look at the two. So we've got diethyl ether, and we've got our nitrobenzene and our aniline. So knowing that the NH2, when it's treated with acid, can be protonated, we would mix in some acid with it and then separate out the layers. Okay, so the aqueous layer that goes in with the acid would then dissolve your protonated NH3 plus, because you've got that R group coming off it, and then your nitrobenzene would not be charged and would stay in your ether layer. Okay, so that'd look like that. And then you want to deprotonate this by treating it with base. Okay, and then that would go into your ether layer, and then you would have two different ether layers, one with your nitrobenzene and one with your aniline in it. Okay, so we're using the fact that we know that amines, when they're treated with acid, become charged. Then to get rid of the charge, we treat them with base and they become neutral again. When they're charged, they can go into a aqueous environment. When they're not charged, they go into an organic environment. So using this chemistry, we can purify compounds quite easily. Okay, let's have a go at a concept check. So which starting compound could you use to make N ethyl cyclohexyl amine using reductive amination. So this is what we're looking at here. So which starting compound could you use? Okay, so looking at our compound here, we have a cyclohexyl ring, or we have a methethyl substituent coming off it. So the easier way to go about this would be to start off with a carbonyl on the cyclohexyl ring, okay, and then acting as the amine, we have NHCH2CH3. Okay, so this should be NH2CH2CH3. Okay, so there's a hydrogen short on this one here. So basically you just put your hand over this side of the molecule and you look at this one here and you add an extra hydrogen to it, and that would be your reagent. So let's have a look at another example. So how would you prepare diethylamine from NH3? So what would we use to make diethylamine? Okay, so this one's a little bit trickier because we're starting with NH3. So we've got to use NH3 to make a reagent that we can then use. So we could use NH3 and react it with an ethyl, with a halogen on it. Okay, so two of these, then we would have the displacement of the halogen to the nitrogen, and we would get the N with the CH2CH3 coming off it. Okay, so this reaction again is a substitution reaction. Okay, one more. So how would you synthesize N-methyl-2-phenylethylamine using reductive amination? So this is what we want to make using reductive amination. So one of them will be a carbonyl. Okay, so possibly this side here would be the choice. So having a carbonyl here, and then you'd have NH2CH3. Okay, so this is your carbonyl on that side, and NH2CH3 is your reagent, and sodium borohydride to get your compound. Okay, another possible way is to use this as your carbonyl, and then bringing in this group here, so formaldehyde and phenethylamine, but probably not the best. Okay, so generally you have your carbonyl on the larger group, but you work with whatever you have in the lab at the time. Okay, so amide bonds are the bonds that link your amino acids together. So they're formed via a condensation reaction. Okay, so you've got your carboxylic acid, you've got your NH2 with your R group attached to it, and you have the condensation. Okay, so water being a product, and you have your amide being formed. So the geometry of the amide bond is essential for secondary and tertiary structure of peptides and proteins. There is limited rotation around that bond. Because of this limited rotation, you can get cis or trans amide bonds in your peptides. So generally we get our trans bond rather than our cis bond. So cis is when these CH3s are on the same side, and trans is when they're on opposite sides. So the reason we generally get the trans one is because of the steric hindrance around that molecule. So it's far more favourable for those CH3s to get as far away from each other as possible. So we get the trans conformation. Okay, so amphoteric amino acids, okay, are usually what we have in nature. So amphoteric means they can act as an acid or a base. Okay, so when they're in there, they're just single amino acids, they can act as an acid or a base, and depending on the pH that they're in, they will have different charges. So looking back just fundamentally what an amino acid is, we've got our amine on the left, we've got our carboxylic acid on the right, we've got our alpha carbon, and we've got our R group, and this R group changes to give you your different amino acids. So at physiological pH, so around about 7, we have a proton transfer from the neutral molecule, and we have our Zwitter ion present. So whenever you have amino acids at pH 7, you have NH3 plus and CO2 minus on the terminal ends. They actually cancel each other out, so it's not really something that you need to think about, because you've got your plus and your minus, so it's still neutral overall. The difference is when you have your side chains. So certain side chains can pick up charges. So your basic ones are your arginine, your lysine, and your histidine, and your acidic ones are your aspartic acid and your glutamic acid. So depending on the pH, you may have a charge on them. Okay, so histidine is one of the basic amino acids, so it looks like this, and histidine can be used as a buffer in your body. And the reason for this is because its pKa is 6. So remember, when you look at buffers, plus or minus 1 pH unit of your pKa is the buffering region, or plus or minus 2 if you want to go 99.9% dissociation. Okay, so pH 6, 7, histidine can act as a buffer. So that's going back to chemistry for living systems there. So let's look at our purines and our pyrimidines. So remember, we showed these rings earlier. We've got our purine ring and our pyrimidine ring. So these are used in our DNA and our RNA. So DNA is your deoxyribonucleotide, and your RNA is your ribonucleic acid, or your ribonucleoside. Okay, so let's get into some of this terminology. So the difference between these two, you can see that we've got a ribo and we've got a deoxyribo. So what that is indicating is that on carbon 2, so this is our sugar, okay, it's carbon 5, this is carbon 1, our anomeric carbon, this is carbon 2. On carbon 2, with a ribonucleoside, we have an OH. On carbon 2, in our deoxyribonucleotide, we do not have an OH. Okay, so you can see we have a deoxy. There is no oxygen coming off carbon 2. So that's where the deoxy comes from. The difference between nucleotide and nucleoside, nucleotide has the phosphate group. Nucleoside does not have the phosphate group. Okay, so deoxyribonucleotide has no oxygen and a phosphate group, and ribonucleoside has no phosphate group but the OH coming off carbon 2. Okay, so we're looking at the general structure. We've got our organic base, we've got our sugar moiety linker here, and we've got our phosphate group that comes on. And I'll show you the reaction on the next slide on how we synthesize these. So our pyrimidine bases are your CTU. So remember, for DNA you have your T, and RNA you have your U. And the pyridine ones are A and G. Okay, so N-glycosides are nucleosides that have glycosidic linkages. Okay, so we've talked about sugars before, so this is hopefully familiar. So how do we make nucleic acid? We start off with a sugar. We then have an amine base, so one of our bases, so one of these guys here, one of our amine bases. They react together under acidic conditions, and we get our glycoside. Okay, and then to make our or our nucleoside, sorry, to make our nucleotide, okay, or our glycotide, we need to add a phosphate. So H3PO4, okay, so then you have your amine, your sugar, and your phosphate group to get that nucleotide. And then joining all those together, you get your nucleic acid. Okay, again, we've talked about this before, but just pointing it out again, biological polymers are directional. Okay, they're directional. So with your nucleotides, your 5' end is your phosphate, and your 3' end is your sugar. Okay. So you can see here, we've got it spelt out a bit more. So we've got our phosphate, we've got our sugar base, phosphate, sugar base. Okay, so this is just with boxes, and this is with the actual structures. So our 5 position and our 3 position. So 3 and 5. So with proteins, we have our N and our C terminal. So N is where you have your nitrogen exposed, and C is where you have your carbonyl exposed. Okay, and your 5 and your 3. Okay, so that is the lecture for today. Hopefully that was clear for you. If you have any questions, come see me in my office. Again, it's the last organic chemistry topic, so next week we're going to be doing revision. Okay, and thank you very much for your attention.